In this last section, we're going to look at the algebraic methods behind finding the values for definite integrals. And so these are where all of our properties are going to come in. And a lot of these properties are going to be the same as the ones that we had for indefinite integrals, except now we're going to have limits on them. Okay? And again, the algebraic methods just means that I don't have to use the definition to evaluate these. So for these, if it just says find the integral or evaluate, then you can use these properties to solve. Again, the only time you have to worry about using that limit definition is when it says to use the definition. Okay. So here again, some of these properties we talked about in the last section. The first being our fundamental theorem of calculus. So I'm just going to put FTC here. That's our fundamental theorem of calculus. It says to find the value for a definite integral, I'm going to find the antiderivative and evaluate it at the upper limit minus the lower limit. Okay. Again, from the graphical representations, we saw that if a is less than b, then the integral from b to a is going to be negative the integral from a to b. And again, from our graphical representation, if I have the same limit, so if I'm trying to find the integral excuse me, over a point, then I know that that area is just going to be 0. Okay. These other properties are ones that come from our properties for antiderivatives. So again, if I have some constant times my function, I can pull the constant out front of the integral and then evaluate. If I have sums and differences, again, I can break them up over the integration. And one of these, we didn't mention this in the last for the antiderivatives because it didn't really come up, but it does not matter what variable I'm using in there. As long as the variable in my function is the same as the variable of integration, I can change that to whatever I want, and then the integral is still going to be the same without changing the limits. Now again, you have to be careful here. The function, notice in both of these, remains the same. And so when we start looking at u substitutions, you have to be careful of that because we are going to be changing the function. Okay? And then this last property just says that if I have an interval where there's some specific point in the middle of that interval, or within the interval, I can rewrite my integral to be separated over the two subintervals. Okay? And we kind of saw this with the Riemann sums. We took an interval and broke it up into pieces and then found the area for each subpiece. And that's basically what this is saying. Okay? So for these basic properties, like I said, they're very similar to what we did with antiderivatives. So let's look at a couple of those. In this first example, I want to find the value of the integral from 2 to 4 of x squared minus 3 over x plus 4. Okay? And so here again, I can treat this like some sums and differences. So I can break this up, 2 to 4 of x squared dx minus 2 to 4 of 3x to the negative 1 dx. That's a negative 1. Plus the integral from 2 to 4 of 4 dx. And here I can see I can apply my properties to get my antiderivative. So in this case, my antiderivative is going to be 1/3 x cubed. I want to evaluate that from 2 to 4. Okay. Notice again, the integral and my dx go away. I get my evaluation symbol. Same thing here. So if I take the antiderivative, I'm going to get a 3 natural log of the absolute value of x. And again, I'm going to evaluate this from 2 to 4. And then lastly, my antiderivative of 4 is just 4x evaluated from 2 to 4. Now again, just like the plus c's when we're doing the antiderivatives, for each piece I'd get a plus c, but I could just make it 1 plus c at the end. Same thing here. You can write each of these individual evaluations, or I can think I'm going to take the antiderivative of the whole thing and evaluate all of it from 2 to 4. Okay? And it doesn't matter which way you go there. You're going to get the same answer in either case. So here, now that I have my antiderivative, I'm going to evaluate it at the upper limit. Minus evaluating it at the lower limit. And I'm going to go ahead and come down a line. So at the lower limit, so from there, I can go ahead and evaluate. So we'll get a 64 over 3 minus 3 ln of 4 plus 16 minus 8/3 minus 3 ln of 2. That's going to become a plus because of the minus and the minus, minus 8. And combining some terms here, for the logarithms, notice ln of 4 and ln of 2, I can get common arguments there. 64 minus 8 looks like 56 over 3. Again, here I can rewrite this. 4 I can think of as 2 squared, so that's minus 6 ln of 2 plus a 3 ln of 2, and then the 16 minus 8 plus 8. So getting common denominator here, I'll have a 24 over 3. Adding to that will give me an 80/3. And then from here, minus 6 of these plus 3 means I'm looking at minus a 3 ln of 2. So there would be my answer for that definite integral. Okay. Here we can do the same thing. So looking at the integral from 0 to 5, e to the x minus 2x to the 1/2 dx. So again, I can think I'm going to take my antiderivative, which is just going to be e to the x minus 2 times the antiderivative of x to the 1/2. So again, we'll add 1 to the exponent, divide by the new exponent. I want to evaluate that whole thing from 0 to 5. Okay. Again, I would recommend cleaning up before we evaluate. So again, I can invert and multiply. We'll get 4/3 x to the 3/2. That's a 0. Okay. Plugging in my upper limit, I'm going to get e to the 5th minus 4/3 times 5 to the 3/2. At my lower limit, we'll get e to the 0 minus 4/3 times 0 to the 3/2. Okay. Some of these you're not going to be able to simplify too much. Okay. In this case, I would probably just leave this as e to the 5th minus 4 square roots of 125 over 3. Here, e to the 0 is just 1. That term is going to go to 0. So there's an acceptable answer for something like Webasine. The square root of 125 I can bring down just a little bit more. So there would be our answer for this definite integral. Okay. For a lot of your definite integrals, you're not going to get nice numbers, meaning sometimes you're going to see some ln's, sometimes you're going to have some roots in there, sometimes there's going to be fractions that can't go down any further. All of your answers should be simplified. You should only give decimal answers on homework and exams if you're asked. Most likely in an exam, you're not going to be asked for a decimal answer. Webasine will accept either. So again, remember, if I'm putting something like this or this into Webasine, you can put it in directly, or you can go ahead and plug it into a calculator and round to the number of decimal places it's asking for. Okay. So here are a couple more examples of our definite integrals using some of those properties we talked about. But more importantly, these are ones that include some of that U substitution that we did back in section 2. So in this first example, we're looking at 5x squared e to the x cubed being integrated from the interval 0 to 1. Okay. So in this case, if I look at this, again, because of the product, I know that I can't use my basic properties directly. And so here, we're going to let u, again, be that higher power, so x cubed. and my differential is going to be 3x squared dx. Now, one of the differences between the u substitution with definite integrals as opposed to just indefinite integrals is that when I go and I change my function from f in terms of x to something in terms of u, I need to make sure I change my limits on my integral. Okay? And so here, if I'm looking at this, if u is equal to x cubed, note that when x is equal to 0, u equals 0, and when x equals 1, u equals 1. Okay? This one is nice in the sense that they came out to be the same, which is not always going to happen. But now when I rewrite my integral in terms of u, everything is going to be in terms of u, including the limits. Okay? And so here, now I just match things up. So I've got my x cubed, I've got my x squared dx. I don't need that 3, but I do need a 5. So I'm going to multiply by 5/3, or divide by 3 and multiply by 5 to get my 5x squared dx. So now, in terms of my integral, u, my limits are again 0 and 1. My e to the x cubed becomes e to the u. The 5x squared dx becomes 5/3 du. Okay. From here, I'm going to go ahead and rewrite it. So I'm looking at 5/3, the integral from 0 to 1 of e to the u du. And then I'm going to take the antiderivative, which means I'm going to evaluate this from u equals 0 to u equal 1. And notice here, I do actually mean u equals. I don't have to go back and plug in for x because I've made the substitution everywhere. So now at the upper limit, I'm going to get a 5/3 e to the 1 minus at the lower limit 5/3 e to the 0. And then evaluating, e to the 1 is just e, and e to the 0 is just 1. So there is my value for my definite integral. Okay. Now, with these, you have the option of going back and plugging in for x. And like I said, in this case, it's very nice because if I go ahead and substitute my limits, I don't have to go back and plug in for x. But if you don't want to, find these limits in terms of u, then at this stage, I can't put limits on here because those are going to be limits in terms of x. And then when I get down to this stage to go and evaluate, I have to rewrite back in terms of x before I can plug in my values. Okay, so in this example, let's try it without the substitution of the limits. Okay, so here again, first thing I notice is I've got a quotient, which means I'm not going to be able to use my basic properties. So u, in this case, again, will take the higher power, which is basically x to the 4th plus x squared plus 1. We'll notice that denominator is not written correctly, so we'll rewrite it as we go. My du is going to be 4x cubed plus a 2x. And again, don't forget my dx on that. Almost what I need, but I've got double what I want. So I'm going to take half of that to get my 2x cubed plus x dx. Okay. Now for this one, like I said, we're not going to plug back in. We're not going to substitute the limits. So here, when I rewrite my integral, I'm going to leave the limits off, okay, and I'm going to put everything in terms of u. So we'll have the 1 over u times the 1/2 du. Again, I can bring that 1/2 out front. And take my antiderivative. Okay, and again, because I don't have limits, I do want the plus c there. Okay, but then, when I go to plug back in, I want to evaluate in terms of x. So in my next step, when I plug my x's back in, meaning the x to the fourth plus x squared plus 1, I'm going to evaluate this, because that constant is going to be determined by the interval. It's going to be evaluated from 0 to 1. Okay, so there's a couple things happening here. If I don't make a substitution on my limits, I can't put limits on my integral. And without those limits, I need to make sure I have a constant of integration. But when I substitute back in for x, I'm going to take care of that constant of integration by putting the limits back on there. Okay? And then from here, I'm going to go ahead and evaluate. So 1/2 the natural log of my function evaluated at the upper limit, which looks like 1 plus 1 plus 1, minus 1/2 my natural log evaluated at my lower limit, which looks like 0 plus 0 plus 1. Simplifying, looks like 1/2 natural log of 3. I can drop the absolute values because 3 is positive. And over here, natural log of 1 is just 0. So there is my value for my definite integral. Okay. And so between the two of these, you can kind of see you'll get the same kind of answer in the end. Both of them are going to turn out to be a number. Both will work for any function that you're looking at. It's just up to you whether you're going to keep everything in terms of u or you're going to keep things back in terms of x. And so you'll have to decide which way you like to do that. Okay. In this last example, I'm going to do one more where we switch the units. Okay. So here again, I've got a 2e to the negative x over e to the negative x plus 1. And I want to evaluate that from negative 1 to 1. Okay. And so here, again, if I'm looking, I'm going to need a u substitution. Again, I've got some fraction in there, so my basic properties don't quite hold. In this case, top and bottom have the same degree. So it's a little harder to pick which one's going to be my u. But if I think about, again, the derivative of a constant times e to the negative x, it's just going to have a sign change from the negative x. But down here, I'm not going to be able to get that plus 1. So here I'm going to let the bottom, again, be my u. Taking my differential, it's going to be a negative e to the negative x dx. Okay. Don't need the negative, but I do need a 2. Okay. So I'm going to change the sign to make everything negative, and I need to multiply through by 2. Here again, I'm going to change my limits. So when x is negative 1, we can see we'll plug in, we'll get e plus 1. And when x is 1, we see that u is going to equal e to the negative 1 plus 1. So rewriting my integral, it's going to be e plus 1, e to the negative 1 plus 1. My e to the negative x plus 1 on the bottom is my u. The top 2e to the negative x dx is negative 2 du. So I'll pull that negative 2 out front, take my antiderivative, and I'm going to evaluate that at my limits. Okay. So at my upper limit, negative 2 natural log e to the negative 1 plus 1, minus at the lower limit, negative 2 natural log e plus 1. I can simplify these. So notice there's a 2 that's going to pull out front. This term will be positive, that one's negative. So subtracting logarithms says it's going to be the log of the positive one over the negative one. And notice there I drop my absolute value because both my terms are positive. E to the negative 1 plus 1 and e to the 1 are both positive values. Okay, so there's my value for my logarithm, or my integral.